Hello and welcome to video 6 of 8 in the FP3 chapter Integration. If you've got time, pause the video now and think, how would you integrate each of these four things? Hopefully the first one is fairly easy. Direct integration from sine, you know the standard result. Sine squared, you probably thought use an identity, turn that into a cos 2x of some sort. Sine cubed we've talked about before, you can split this into a sine times sine squared and then replace the sine squared with a 1 minus cos squared, expand the brackets and use some standard results that we've talked about in previous videos. And hopefully the last one, you perhaps thought to yourself, I don't know. Maybe split this into 3 lots of sine squared and replace each one with an identity like you did here. Expand out. It could get a bit messy, but maybe it would work. I say hopefully you're not sure on this one, because if you're sure on this one, there's probably no reason for you to watch this video. This is the sort of thing we're going to talk about in this video here. And to do this, what we're going to do is something called a reduction formula. Now be aware, this video is a little bit longer than these ones were, because these 3 were based on ideas that you've seen before. So you've done substitution before, completing the square, and integration by parts. We were just applying them to this chapter. Here, reduction formulae, you've probably never seen this before. So I'm going to go through the idea of it and some examples, and some of them take a bit of time. So brace yourself. So when we're integrating higher powers, that's the problem here. Sine to the power 6 is harder because it's a higher power. We can use certain techniques. Like I said, maybe you could split it into sine squareds and replace those by 1 minus cos squareds or by a cos 2x. But to do that, it becomes quite lengthy and, the word I've used there, onerous. For example, this one here. You could solve this by using integration by parts. And each time you applied integration by parts, if you chose the right way around, this x to the 4 would go down a power until eventually it disappeared and you would just have e to the x on the end. But it's a lengthy process doing that 4 times. So the question is, how are we going to solve this without doing all that work? And the short answer is, we're not going to solve it without doing all that work. We are going to do all that work. We're going to apply integration by parts 4 times. But the longer answer is we're going to try and condense it by using the repetition, because every time you apply this, you get something that's very similar to the thing you started with, and you're doing a very similar integration by parts process each time. And if we can use that repetition to shorten the process by applying a pattern, then we can cut a bit of time off of it. Now that might not seem like a very good answer, because it's still going to be quite lengthy and you're still going to have to do the basic work of integrating something like this. But if you think, if this power here was a 40 rather than a 4, or if it was a slightly more complicated pattern, then I hope you can see that it is cutting down the time. And from a computer programming point of view, programming in a reduction formula, I think, would be easier than programming integration by parts. So that's what we're going to do. And to do this, the idea is finding a relationship between the integration that we're starting with the power n, and a similar integral with a smaller power, sometimes n minus 1, maybe sometimes n minus 2, and connecting the two to give us a pattern that we're going to call a reduction formula. And often it will involve integration by parts, but I've tacked on an example from the book at the end where that's not the case, because it doesn't always. But usually this is a good place to start, trying to do integration by parts. So I'll go through the idea on this slide and then I'll apply it on the next one, and you can see how the general process works. So looking at x to the n, e to the x, if you were to apply integration by parts, you would want the x to the n to be the u term, because you differentiate that, and each time you differentiate this, the power reduces. And e to the x would be the dv by dx term. And when you integrate that, it doesn't change. And if you apply the formula, it's up here in the corner, we're going to be using this a lot. If you apply that, you get this. And the key to this idea is that this integral is very similar to this one. So if we pull the n out of there and make it look like this, then you could just say, hey, if I want to integrate this, it's basically the same as this, but instead of n here, here, and n minus 1 here, it would be n minus 1 here, here, and n minus 2 here. And that's the idea we're going to use. We're going to formalize it by writing it out, but that's the basic principle. And if we use some notation here, if we say the original integral with the power n is in, I for integral, then this integral here is the same thing, but with n minus 1. So I can write this as in is equal to part of the integration here, x to the n, e to the x, minus n times the same general format, but with an n minus 1 instead of an n. And then I can do this process as many times as I like. And I'll show you what I mean by that on the next slide. So this is what we had. We had this for this integral here. The reduction formula is this. And when I say apply it as many times as we like, what I mean is if we actually have an integral, let's take the one we had before, x to the 4 e to the x, then this becomes I4. And I can apply this formula, the reduction formula, I4 is equal to x to the power n, where n is 4, e to the x, minus n, where n is 4, I, n minus 1, so that's 3. And that by itself doesn't help. But the point of this is that we know what I3 is as well, because I can just put a 3 in this reduction formula. So that becomes x to the 4 e to the x minus 4 lots of I3, which is x cubed e to the x minus 3 lots of I2. And you can see where I'm going to go with this. If we expand that out, you get plus 12 I2, but I2 is x squared e to the x minus 2 times I1 by putting 2 into the reduction formula. And then we've got I1, but we can put 1 into the reduction formula, and we can keep going. So let's expand that out. X to the 4 e to the x minus 4x cubed e to the x plus 12x squared e to the x minus 24I1, but I1 is x e to the x minus 1 times I0. Now, we've got I0, but I0, if you put a 0 into the reduction formula, x to the n becomes 0, and there's a 0 times this, so what we're going to have to do is go back to the original idea and put 0 in here instead, because the reduction formula is going to break down at some point. And that is when this becomes x to the 0, which is just 1. So I0 is just the integral of e to the x, which is where we expected this process to finish. So instead of I to the 0, I'm going to write integral e to the x dx. So we've got x to the 4 e to the x minus 4x cubed e to the x plus 12x squared e to the x minus 24x e to the x plus 24 times the integral of e to the x is e to the x, and of course a plus c on the end. So the integral of x to the power 4 e to the x is this. So as you can see, it's not a short process, it's still quite lengthy, but doing, I guess you would call a general term, a general answer, and then being able to apply it each step cuts out all of the actual process of doing integration by parts. Instead of doing it 4 times, I've sort of done it once and then applied the same pattern again and again. So that's the idea. The problem comes, in terms of problem solving for the questions that we're going to do, when you actually need to create your reduction formula. The one we did there was not too bad, but sometimes it can be quite involved to manipulate it to get your original integral with an n connected to an integral with a lower power, n minus 1, or it might be n minus 2, or it might be n minus 3, something with a lower power, so that it is slowly getting easier down to a final result. And manipulating that to get your reduction formula in the first place can be quite difficult. But once you've got it, it cuts out most of the integrating work that you would have had to do if you weren't going to use this method. So a couple of examples on this, because the more of these you see, the more methods you get used to, the easier it becomes to recycle those methods in new problems. So here's a good example. Show that if we call this integral here n, then this reduction formula is true. And there's a little caveat there that this is for n is greater than or equal to 1. So when you get down to n is equal to 0, if you were to actually apply this formula, which we don't have to do in this question, but if you did, then you wouldn't use this. You would go back and put n equals 0 into here, and that would be where you stopped, like we did in the previous example. So the question is, can I actually get this reduction formula? So if we start with 0 to 1, x to the n, square root of 1 minus x dx. Now here, if it's fairly obvious that you can use integration by parts, go for it, because most of the time that will be a good starting point. And as with the previous one, we've got an obvious u and an obvious dv by dx. Because if we try to make this u and differentiate it each time, the problem is not going to get easier. But if we make this term u, it will eventually get down to this term going away and just leaving us with this, which we can integrate. So I'm going to make x to the n u. Try and save space, I'll do that up the top here. So u is x to the n, so du by dx is nx to the n minus 1, dv by dx then must be 1 minus x to the half, and if I integrate that, I get 2 over 3 minus 2 over 3, 1 minus x to the 3 over 2. I'm assuming that that's okay, I don't need to explain where that came from. Now we're going to apply the integration by parts formula and see what we get. So I have u times v, so I have minus 2/3 from the v, x to the n from the u, times 1 minus x, the 3 over 2. Now quick note here, we do have limits, so I do need to apply those here, and in many times this will be a good thing, because often this will make this bit much simpler. We'll talk about that in a second. I'll keep going for now with the formula. Minus the integral from 0 to 1 of v times du by dx. So we've got a minus 2/3 from the v, we've got an n x to the n minus 1 from the du by dx, and then we've got the rest of the v. I'm writing it like this just because I like my numbers first, and then my powers of x, and then my brackets. But I hope you can see that this is v times du by dx in here. Okay, now for the good bit. You can see, I hope, if we put a 0 in here, 0 to the power of anything, all of this will be 0. And if we put a 1 in here, 1 minus 1, that's a 0, all of this will be 0. So when you put your limits in, this entire term here, the full term, all becomes a big fat 0, which is great. That all simplifies away to nothing. Now I've got the problem of making this thing look in the form of this thing. Because if it doesn't, then I can't use in, and what I'm trying to do here is in minus 1. At the moment this won't work because I've got a minus 2/3 n, that's not here. The x to the power n minus 1, that's okay. It's different, but I'm expecting that to be different. The n changes to an n minus 1. But this bit here is a problem as well, because that is not 1 minus x to the half, this is 3 over 2. So the easy bit first, I can pull this out the front. Minus 2 over 3n, I can change that into 2 over 3n in front of the integral. And then we've got x to the n minus 1, that was okay, we want that. And then this bit here. I'm going to have to split this into two pieces because I must have 1 minus x to the power half. I need that in my integral. But the problem is we've still got the 1 minus x. I can't just get rid of that. I can't just delete it. It's still there. So we've still got this problem. How do I connect this to this in order to replace this with in on the left and this thing here with in minus 1 on the right? And the trick here is actually quite simple. Once you've got to this point, just expand this bracket out. 1 times all of this, and minus x times all of this. So I'll do it in two different colors here to make it nice and clear what I'm doing. Let's do the one in red, and I'm running out of colors. Let's do the minus x in white. So we've still got 2/3 n in front. And then if I expand this bracket with the 1, I've got integral x to the n minus 1 times the square root of 1 minus x dx. Great, that is looking like something I can use. Then I've got a minus from the minus x, 2/3 n still, because I'm splitting this into two completely separate terms. And then I've got the integral of x to the n minus 1 times x, brings us back to x to the n, times the square root of 1 minus x. So this times by the x gives you this, and then we've still got 1 minus x inside the square root here. Now I hope you can see that this is exactly in this form except for the n minus 1. So I can change this into in minus 1. And this bit in white is exactly the same as this. It is identical to this. So this bit in white can be written as in. And of course, the bit on the left can also be written as in. Now really I should have been keeping my limits in here. Let me just quickly put these in. And then we've got 2/3 n times in minus 1 minus 2/3 n times in. And that is all equal to in on the left. But of course this doesn't quite match what they've given us here, and we should always finish our working with exactly the same thing as is written in the question if we're trying to show something. So I need to rearrange this, and I just do that by putting this on the other side and factorizing out the in. So I'll change everything back into green now. So we've got 2/3 n in plus in is equal to 2/3 n in minus 1. Oh, sorry. Where did that come from? That should be a small n minus 1. Multiply everything by 3, factorize out the in, gives me in 2n plus 3 is equal to 2n in minus 1. Getting smaller and smaller here to try and fit it on the screen. So in at the last is equal to 2n over 2n plus 3 times in minus 1. And that is exactly how they want it. So there's a lot of work there. Fortunately, in this question, we don't then have to use it. We just had to show the reduction formula was this. This is a very useful trick. This is one of the methods that you'll use in different questions. So take note of that. Okay, the second example. Slightly different. A trig example. Derive the reduction formula this. Again, they're putting a caveat there. N must be greater than or equal to 2. And when it isn't, you then have to put the n back into the original to see what the integration is you've got at the end. And then part B, we're going to have to use it to find the value of this and the value of this. Okay, the difficulty here then. This is not obviously an integration by parts process. On the one hand, that makes it difficult because you might say, oh, I can't do it. On the other hand, if you remember what we did in a previous video, you might start thinking, oh, there are many different ways that I can do this. Because if you remember, we had on the inverse trig, you can change it into 1 times sine to the nx. But if you can do that, then you could also do sine x times sine to the n minus 1x, or sine squared x times sine n minus 2x, or sine cubed x times sine n minus 3x, and you see where I'm going with this. Once you realize that you can force this to be a product of two things, suddenly you realize as well that you've got many different options. And not all of these are going to give you the answer you want, because many of them you'll just get stuck in a whole lot of maths that just doesn't work in terms of actually getting a reduction formula at all. So this is another case of, if I show you this process, you might be able to then use it in subsequent problems. So it's a case of practice as many of these as you can, so that when you come across something you haven't done before, you might at least have done something like it before and have an idea of where to start. Because if you don't know where to start here, this can be a very difficult question. In this case, if you go through and you try these different ones, I hope you'll find that this one here is the best one to choose. I know that from experience. Okay, so if I use u is equal to sine n minus 1x, and dv by dx is equal to sine x, hopefully this will work. Of course, the other problem is you might have switched these around. You might say, oh, well, I want dv by dx to be sine n minus 1x. But if you could easily integrate that, you could probably easily integrate this anyway. And if we differentiate this, the n minus 1 will come down, and there's a little clue in the question here that we'll get an n minus 1. So I'm going to stick with this. So if I integrate sine x, I get minus cos x, and if I differentiate this, I get n minus 1 times sine to the power of n minus 2x times the derivative of sine, which is cosine x. And then I can apply the formula in white at the top here, as normal. So that is going to equal u times v. So u is sine to the n minus 1 x, v is minus cosine x. And again, we've got the limits, so we need to put these in. And again, this is a good thing, because if you have a quick look here, sine of any power of x where the x you're putting in is 0, that will be 0. So everything will be 0. And cos of pi by 2 will be 0, so everything will be 0. So all of this is just going to become a big 0. Great. Minus the integral from 0 to pi by 2 of v times du by dx. So we've got minus cosine x times n minus 1 sine to the power of n minus 2 of x times cosine x dx. And we have this same problem that we had before. This does not match this form. So if I try and change this into in, it does not look like this is going to change into in minus 2 as we've got here. So part of my problem solving is I need to make this look in this format somehow. And I can take out the minus, that's okay, that becomes a plus, that's nice and useful. Cosine times cosine is cosine squared, so what I've got here overall is positive 0 to pi by 2 cosine squared x, and I can pull the n minus 1 in front of the bracket as well. I should have done that. And sine n minus 2x dx. So the n minus 1 is there, great, but all of this is equal to this, which is in. We don't have an n on the left yet, so something funny is going on there. And I certainly don't have this looking like this just yet, with this cosine squared there getting in the way, so I can't change it into this yet. So I need to get rid of this cosine squared. To do that, I can turn that, let me be clear, this is in on the left. I can turn this cosine squared into a 1 minus sine squared. And perhaps you can already see how this is going to help, because if I multiply out the 1 here, we'll have sine to the n minus 2, which is what this is going to be. And when I multiply this by sine squared, it brings me back to sine to the power of n, which is what this is. So similarities with the previous example, we're going to have an in on both sides of the equation. So I've expanded this bracket and split it into two separate terms. And now you can see that this integral is the same as this. Well, I won't write all the limits on, but of course all the limits are still there. So this can be written as in, and this is in exactly the same format, but with an n minus 2. So this is n minus 1 times n minus 2 minus n minus 1 times n. And on the left, in. And same with the previous example, we now need to manipulate this just to make it exactly in the format given in the question. So if I expand this second bracket out, you can see that the in's will cancel, and the minus in goes on the other side. And we have our final answer. So in this case, the sneaky trick here initially is to split sine power n into sine times sine to the power n minus 1. Then split your, or not split, substitute your cosine squared with 1 minus sine squared. Okay, to make room for the next part, I'm going to clear all of that off, but we have the final answer here in the question still. So part B, apply this to deduce the values of this. Now be careful here, the limits must match. If these limits were different, it would be a different sort of question. So here, sine power 5 of x, that is when in is I5. So if I rearrange this very quickly, in, because we don't want the n on the left here, n minus 1 over n, n minus 2. So this is the reduction formula I'm actually going to use. So this becomes I5, which using the reduction formula is 4 over 5 times I5 minus 2 in this case, so that's I3. But I3, we can apply the reduction formula, is just 2 over 3 times I1. And I1 in this case, remember n must be greater than or equal to 2. So I1, I now have to put a 1, sorry, not in here, in here. So it's just a sine x. So that is equal to 8 over 15 times the integral of sine to the power 1 x from 0 to pi by 2, which of course is, I was going to say cosine, minus cosine x, 0 to pi by 2, and pi by 2 is a 0, cosine of 0 is a 1, but that's a minus, so we get, and that's in the minus, so it becomes a plus again. So if you put all of that in your calculator or work it through, you will get 8 over 15, because it's the upper limit minus the lower limit. But when you put this in here, you'll end up with a 1, and 0 minus minus 1 is 1. Final part, if it's a power 6, very similar, we get I6, which is equal to 6 minus 1, 5 over 6 times I6 minus 2 is 4. Follow the formula again. So it's I4 now is 3 over 4 times I2. And I2 is 1 over 2 times I0. But we can't put I0 into the reduction formula, so it goes in here. Sine to the power 0 is 1, so we're just integrating dx. So on the top we've got 15 over 24, 48 times the integral from 0 to pi by 2 of dx, which is just x. So when you put that, let me write it out. We've got 15 over 48, that is 5 over 16 times x from 0 to pi by 2, which of course is just pi by 2. So we end up with 5 pi by 32 as our final answer. So although it was difficult to prove this initially, I hope you can see the power of a reduction formula once you've got it to make something like this or this much easier to calculate without going through integration by parts 3 or 4 times. Okay, the final example is to show you that you don't always need integration by parts. If you're not going to use integration by parts, usually the alternative will be using an identity. And in this case, the question tells you what to do. So this is the case for in, and then it says by writing this as this, which we have done before, we split our sign into something similar, and using this, establish the reduction formula this. So what we did before was split our sign into two parts and then use integration by parts. But in this case, we're going to use an identity. So follow what the question says, and hopefully it will become clear why we don't need integration by parts. Let's try. So they're saying write this as tan n minus 2x times tan squared and then replace the tan squared, presumably, because they've told us to use that identity. So we'll replace that with a sec squared x minus 1. And as with a number of the other examples, if this doesn't match what you need it to match, expand the brackets. That's a good option at this stage. And put it into two big integrals. So we've got tan n minus 2x times sec squared x dx minus the integral of tan n minus 2x dx. And straight away that has helped because this matches this format. So I can change this into I n minus 2. But this does not. However, if you remember your standard integrals, we can integrate this directly. We can do that because if you think of this term as being a tan x in a bracket to the power of n minus 2, then the thing in the bracket here differentiates to give the thing outside the bracket. So this has come from a tan to the power n minus 1 x. So if I put that over here, tan n minus 1 x. So if you differentiate that, you get something very, very close to this. And in fact, the only difference is that n minus 1. So that is equal to tan n minus 1 x, and in order to balance that, I need to divide by that power minus integral tan n minus 2 x dx. And we're basically there now. The left hand side in, yes. The right hand side 1 over n minus 1, I'll just write that the same way they've written it, but that's effectively the same thing. And this is in minus 2. So we've got the reduction formula without using integration by parts, because the integration here was a standard integration technique. But of course, that's only standard and easy to do if you see it. And it's not always easy to see these things if you're going through the process and you're thinking, oh, maybe integration by parts, oh, maybe identity. It's, again, let me say, practice. The more of these you can practice, the more different ways of solving them you'll see, the more likely it is that when you come to do a new one, you'll have an idea of what might work and what might not work. So to help you with that, of course, are the questions in exercise 4F in the textbook, but be aware, because of the process being quite lengthy, and also the problem-solving element where you might choose the wrong method initially, these will take you some time. And what I mean by some time there, of course, is lots of time. So spend a bit of time doing these, and maybe I'll see you in the next video.